Okay, so we just went through the equation for induced EMF, and induced EMF is equal to negative n is the number of loops, times the change in my magnetic flux. And so that change in magnetic flux can be from a change in my magnetic field, it could be a change in the size of my loop, the area of my loop, it could be a change in the orientation, and it also is affected by like how quickly that change is occurring. So this kind of tells you like how the magnitude of the induced EMF is affected. Let's talk now about this negative idea. This negative idea is described by something called Lenz's law. Okay, so Lenz's law says that when a loop of wire is in a changing magnetic field, a current's going to be induced to oppose the changing magnetic field. So the negative is indicative in that the eventual resulting electrons that are going to move, they're going to move such that they go against however it was that change happened. Okay? Induced EMF is only created if we have a changing magnetic field in a given region. And the electrons that are going to subsequently move because of that EMF are going to move to go against that change. Okay? So this is kind of like the textbook definition of Lenz's law, but I want to kind of break down like what is happening play by play, moment by moment as my magnetic field is changing or my magnetic flux is changing. Okay? So effectively, the first thing that's going to happen is that the magnetic flux changes. Okay, so that's like the initial step. That's the driver. So the magnetic flux changes. So one of these factors is changing. Either my magnetic field, my area, my orientation. It's changing in a given amount of time. So the magnetic flux changes. And we said that if you have a changing magnetic flux or a changing magnetic field, you're going to create an electric field. So the next step, or kind of the consequence of this, is that an electric field is created. And we know that electric fields cause electrons to move. So this is going to cause any electrons in a nearby conductor to move. It's got to be a conductor because conductors, they allow the electrons to kind of freely move within them. So if I have a wire and there is a changing magnetic field nearby, there's going to be a new electric field. If all of a sudden there's a new electric field, those electrons are going to be like, hey, I want to go against that new electric field. Okay? So any electrons in the nearby conductor are going to move. And we know that if electrons are moving, electrons are going to create their own magnetic field. So these electrons create their own magnetic field. So in effect, this is an induced magnetic field. And in fact, right here, this causes any electrons to, in a nearby conductor move. This is an induced current. Because anytime you have electrons moving, we call that a current. So this induced current is going to create its own magnetic field. We'll call this induced magnetic field. This induced magnetic field goes against the change in the original magnetic field. So this is what that negative means, and conceptually, it's pretty meaty. So I want to go through a few examples of kind of this process. And this is the actual steps that occur. The magnetic flux changes. This creates an electric field. Electric fields cause electrons to move. Electrons moving create magnetic fields, and this magnetic field essentially opposes this real change. So this is like the play-by-play, but when we go to analyze problems, sometimes it's helpful to look at this and then instead go to the end and kind of see like, well, what does my induced field look like And then what does that induced current look like that's causing that? And then what does that electric field look like? Okay, so even though this is the order in which things physically happen, it's a lot easier to analyze it going the other direction. Okay, so I'm going to do two examples. They're rather conceptual in nature, and they don't really look like, you know, your typical problems. I think I can move that just a little bit over. Okay. I'm actually kind of running out of space here. So in this example, I have a magnetic field that's going into my board, and I have a loop of wire here. And so my magnetic field gets stronger. So something happens, I'm going to move this a little bit here. Something happens where my magnetic field gets stronger, and I have lots more magnetic field lines going into the board. So if I look at kind of like my initial scenario, and again, this is just kind of conceptual. Initially, I have two X's, two magnetic field lines going in. Like that's my magnetic flux. And then when my magnetic field gets stronger, now I have approximately 9 X's. Okay, so my magnetic flux increased. Now, it's going to set off a chain reaction of events where my magnetic flux changes, so I'm going to create an electric field. That electric field is going to cause some current. That current is going to create its own magnetic field. That magnetic field is going to oppose the change. So let's start here. The magnetic field that gets created here is going to oppose the change. I had 2 field lines going in, and now I have 9 field lines going in. It's going to oppose the change. And so my induced field is going to be created such that it opposes it. It's going to try to make it go back to only 2 magnetic field lines going in. So we actually end up creating, conceptually, I'm just going to say, we create 7 magnetic field lines that are going out. So we create 7 out, 7 dots, so that I have overall 2 X's. I have like what I had before, okay? This is the idea of my new field line is going to oppose the change. I increased by 9, right? Rather, I increased by 7. I'm going to try to oppose that. So I'm going to create 7 dots to oppose those X's. So if I have this new magnetic field that's coming out, I'm going to use right hand rule number 1, where your thumb is going in the direction of your current, your fingers curl around in the direction of your magnetic field. You can actually do the opposite, where your fingers curl around in the direction of current, and your thumb is going to go in the direction of magnetic field. So if we do it that way, if for my induced magnetic field, if my thumb, my magnetic field is coming out, like so these are my new field lines that I created. If they're coming out of the board, then the current that's got to create that has to go counterclockwise. The current that's creating this new magnetic field has to go counterclockwise. So in terms of play-by-play, what happens, I have this initial situation where I have this magnetic flux of 2 magnetic field lines going in. The magnetic field increases, it strengthens. So all of a sudden, boom, my magnetic field strengthens. It creates an electric field. That electric field causes electrons in this wire to move counterclockwise in this wire, and as they move counterclockwise in this wire, they create a new magnetic field, and the new magnetic field is opposing the change. It's opposing the increase, okay? So it's seeking to oppose the change. That doesn't always mean that my new magnetic field is going to go against the original, and I want to show you an example of that, okay? The new magnetic field is opposing the change, so it wants it to go back to the way it was. So if we see my magnetic flux is decreasing, we actually end up going in the same direction as the original. So here's my second example. Very similar in that I've got magnetic field lines going in, I have my loop of wire, and then all of a sudden something changes and my loop of wire gets small, really tiny in this area, so my area vector is shrinking in size. So if I were to do a comparison, if I were to do like a before and after, before I have approximately, again, this is just conceptual, I have 4 going in, so there's another way you could represent it, 4 going in, and now I only have 1 going in. Well, I want it to be like it was before, and so what am I going to do? I'm going to induce 3 going in, so so that the magnetic flux is similar to what I had before? Well, if I'm going to create 3 field lines going in, right-hand rule number 1 is going to show me the direction of the current that creates those magnetic field lines. And so, again, right-hand rule number 1, you can do either your thumb is your current or your thumb is your magnetic field, and then your fingers are just going to be the opposite variable. So in this case, if my thumb is my magnetic field, my induced magnetic field is going in, then my current has to be clockwise to create those induced magnetic field lines, okay? So again, actual play-by-play, here's my magnetic flux. I've got a bunch of field lines going into my loop. All of a sudden, my loop decreases in size. I then create an electric field. That electric field causes electrons in this wire to move. The electrons in this wire go clockwise direction to induce a magnetic field going in to oppose the decrease in my magnetic flux. Okay? So that is where this negative factor plays in terms of what direction is your current going to flow to then oppose the change. You're going to see when you actually do the calculation, if your magnetic flux, if this delta VA cosine theta delta T, if this term is negative, your final answer actually comes out to be positive, and that positive nature will tell you that your induced magnetic field is going to create your induced magnetic field is going to go with the original if this induced EMF is positive. If your induced EMF is negative, that means you're going to create a new magnetic field that is going to go against the original. And when we do mathematical examples, and we'll kind of see that play out, hopefully that'll make it a little bit more concrete with the conceptual aspect of Lenz's law.